Hello, so let's get into exponents and let's not worry about it too much because it's actually much easier than it's portrayed in the textbook. So we're going to look at their first page, which is just things, concepts you need to know, and we'll just copy and paste it. Now, before I get into it, let's start with some basics. We're going to go backwards here. Unfortunately, we're mostly dealing with multiplication and division. We are dealing with some addition and subtraction, but it's actually in the exponent level. We're never really adding things together. But let's look at some very basic. So first of all, you're going to have to get comfortable with just exponents, right? 6 to the 3, 7 to the 4. Doesn't matter what the exponent is, I'm just doing it. Tens obviously are the easiest exponent. But let's get into the simplest way to think about them. 5 to the power of 2 is simply 5 times 5. And we use powers because we don't want to write 5 times 5. Just as we use multiplications. When I say 5 times 4, I'm actually saying 4 plus 4 plus 4 5 times. That's all I'm saying. Well, we came up with multiplication to save writing this. And we came up with powers to save writing time doing this. So each thing is just a notation to save time. Instead of writing 5 times 5, we just say 5 to the power of 2. So this exponent really tells us how many times we're going to multiply that number times itself. And I want you to think about that at all times. So we're really saying 5 times 5. And that's obviously easy to figure out. It's 25. Some exponents are not easy to figure out. So when we see 6 to the 3, right away we're not going to know what it is, and I don't expect you to. It's why we have a calculator that has an x to the y component where you can punch in x and then hit this button and then punch in your exponent and hit equals, and will spit out the exponent. But in this case, 6 to the power of 3 simply means 6 times 6 times 6. So the first part is very easy to figure out that it's 36, and the next part is not. Well, you'd have to do long divisions to realize that the first part is 36, next part is 18, 216 is the answer. But it takes long division and some time to get used to, and you're not expected to know that answer. Instead, often the teacher will just want you to write it in a simple form anyway. And 7 to the power of 4, the next example I gave you, is simply 7 times 7 times 7 times 7. Now, the reason I'm doing this is it really helps to think in these terms, as you'll see in adding and multiplying exponents. And of course, 10 to the 4 is actually, people have a very easy time with that one. 10 times 10 times 10 times 10 4 times, but writing it, they're very fast at it. And that's simply because we have 1, 2, 3, 4 zeros. So we know just to write 1, 2, 3, 4. Oh, sorry, there's 4 zeros. I included the 1 in that. And so it's very easy to realize for us that 10 to the power of 4 is 10,000. Now, scientists, again, don't like writing 10,000, and they will also often use scientific notation instead. Like the speed of light is 3 times 10 to the power of 8 meters per second. And that's because they don't want to write a 3 with 8 zeros. They don't want to write that. And 2 in front, that's 8 zeros, and that's the actual speed of light in meters per second. Well, we definitely don't want to bog down our chalkboard or our whiteboard with that. So it helps to think of why we're doing it and how. Now let's go on to some simple rules. Now, again, we will be looking at bases that are the same. We're never going to be looking at 7 to the 3 times 8 to the 4 and finding out a rule for adding these exponents, because the base, 7 and 8, are different. You can't do it because this is essentially saying 7 times 7 times 7, which is 7 to the 3, times 8 times 8 times 8 times 8. There's no number I can write here to an exponent of whatever that represents both these groups. It's impossible. Now I can do it if this one happens to relate to 7. For instance, and I won't get into it, 7 to the 3 times 49 to the 2, well, it turns out, let's break down what 49 is. 7 to the power of 3 times 49, well, that's simple. Oh, well, actually, let's break down what 49 is in terms of 49. It's 49 to the power of 2 is 49. Well, we can break down this 49 even more. And let's break down this 7 to the power of 3. And what that means, it's 7 times 7 times 7. And what does the 49 times 49 mean? It's this, well, we can write that as 7 times 7 for this 49 times 7 times 7 for this 49. So now I've turned them all into the same base, and you're going to need that skill set eventually. But right away I can see I have how many 7s? 1, 2, 3, 4, 5, 6, 7. Because this 49 to the power of 2 represented 7 times 7 times 7 times 7, which happens to be 7 to the 4. And this 7 to the 3 is represented here. Well, when we add them, we see that we have 7 7s. 7 to the power of 7. Oh, I could have just added these exponents. 7 to the 7. So you're going to discover that when we have the same base and you have their exponents, you can just add them. Let's do a couple more of those. Let's look at 6 to the power of 3 times 6 to the power of 2. Now my theory is that I can just add those exponents, keep the base, and it will be the same as 6 to the power of 5. That's 2 plus 3. Well, let's test out that theory. So I'm saying it's going to be equal 6 to the power of 5. Let's just break this down. What does 6 to the power of 3 even mean? It means 6 times 6 times 6. What does 6 to the power of 2 even mean? It means 6 times 6. Now let's look at this. I've got 6 times 6 times 6 times 6 times 6, 5 times. That's the same as multiplying 6 times itself 5 times, or 6 to the power of 5. So when you break down the exponents into what they actually are, you can easily see why this rule came about. Let's look at some other rules that apply. So that's great. So you're saying to me, Peter, that if I'm multiplying, let's say, 2 to the power of 4 times 2 to the power of 3, that's going to be equal to 2 to the power of 7. And then if I break it down into how many 2's are being multiplied and how many 2's are being multiplied here, I'll see that they are actually the same as that number there. Yes, that's true. Now I'm also saying, though, that if you cannot multiply these two numbers because they do not share the same base. So you cannot come up with any number that works with. However, if I find an exponent of 2, let's say 8 to the power of 3, it's not easy to see, but I can break it down and eventually have 2 to the power of a number. Let's break it down. Let's look at what 2 to the power of 4 is first of all. That's the easiest one. It's 2 times 2 times 2 times 2. Let's look at the 8, what 8 is. Well, let's put it all in brackets so that I have it like that. Okay, well, it's 2 times 4. That's right. But can I break down the 4 even more? Yep, it's 2 times 2 times 2, all to the power of 3. What does that all to the power of 3 mean? Well, it means whatever's in this bracket is timesing itself 3 times. Oh, okay. So I'm going to just write it like that instead. So it's timesing itself 3 times. Okay, that's interesting. How many 2's do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So it's really 2 to the power of 13. Let's see if I could have come up with that number, 2 to the power of 13, in a shorter way than I did. This still works. And by the way, I could have added this up quickly by saying, well, it's 3 times itself 3 times. That's 9. 9 2's in this whole area. And 4 2's here. And they add up to 13. Let's see if there's a shorter way that I could have. So I'm saying it's going to come out to 2 to the power of 13. Let's go back and break down 8 in a way that we can understand. So we're going to leave 2 to the power of 4, and we're going to look at 8. I'm just going to put it below. I'm going to look at it. Well, I know, and I'm going to just keep this power to the power 3 on the outside of the bracket. As I just said, 8 is the same as 2 times 4. And 8 is the same as 2 times 2 times 2. If you don't believe me, take your calculator and multiply 2 times 2 times 2. And that's how you always solve these things. Well, 2 times 2 times 2 is the same as 2 times itself 3 times. 2 times 2 times 2, it's 2 times itself 3 times. Well, that's the same as writing 2 to the power of 3. So inside the bracket, I'm going to change my 8 into 2 to the power of 3. Now you might say, well, Peter, I can't really figure out how these relate. I can't really figure out how these relate. Well, let's go back, and again, I'm going to put my 2 to the power 13 in a handy-dandy spot here, and I'm going to look at what this 2 to the power 3 that is then to the power 3 means according to my last thing. Well, my last thing said that this here inside the bracket is simply times itself 3 times. So instead of writing that 3, I'm going to write times 2 to the power 3 times 2 to the power 3. So now I've written it out as itself times itself 3 times. Now I can use that exponent rule. 4 plus 3 plus 3 plus 3. Oh, it's 2 to the 13. Is there a shorter way that I could have come to that same answer? By the way, this is correct. So I figured it out without breaking down the 8s. Is there a shorter way? Yeah, there is. Instead of making it 2 times to the 3 times 2 times to the 3 times 2 to the 3, well, that's going to end up being 2 to the 9, right? That's going to be end up 2 to the 9, just this area here alone, because it's 3 plus this 3 plus this 3. Yes, it is. Let's see if I could have come up with 2 to the 9 in a different way. Well, wait a minute. 2 to the 3 to the power of 3. I'm just looking at that now. Sorry. This thing always have to click it twice. So I'm looking at this here now, right there. Wait a minute, instead of doing 2 to the 9 after adding it all up, I see that 3 times 3 here, when it's an exponent of an exponent, I can just multiply them instead of adding them. Yeah, that's right. So 2 to the 3, again to the power 3, I can just multiply these exponents and make it 2 to the 9. So we can see an exponent of an exponent simply multiplies them. So now I've left with 2 to the 4 times 2 to the 9, and I can just add, because I'm multiplying two things with the same base, I can just add them, 2 to the 13. But if at any time you don't understand what's going on, look at what's going on with the number. So I was saying 8 to the 4, or I think I said 8 to the 3. Well, just break that down. It's 2 times 2 times 2. And what's this one? Well, I'm going to keep that 3 up there and just write it as 2 times 2 times 2 in brackets to the power 3. So this is the same as that. Okay, and all of this simply means times itself, all the bracket, times 3 times. Well, there's 3 2's, 3 times, so there's going to be 3 more 2's, 3 more 2's. So I got times 2, 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 times 2. So that's 3, 3, and 3. So that's 9 times here and 3 times there. So that's now 12. Now, I know we had 3 to the 13 before, but I think that's because I had 2 to the 4 over here. But it doesn't matter. It will still add up properly. So no matter what you do, you can always break it down, or you can just follow the rules that we just established. Let's go back to those rules and say, instead of changing my 2 to the 3, let's just leave it. And we're going to break down the 8 in terms of 2. Well, that's 2 times 2 times 2, all to the power 3. And I know 2 times itself 3 times is 2 to the power 3 to the power 3. So this here represents the 8, and this here represents the original exponent. Well, instead of figuring it out, I can just, it's an exponent of an exponent, so I can multiply them. So that becomes 2 to the power of 9. So I've got 2 to the power 3 times 2 to the power of 9, and I know that can equal 2 to the power 12. Now that's an advanced lesson, but it's to show you that if you find something in here that relates to that you can express in terms of this, you can then use the rule to add the exponents to come up with the ultimate one. What about other numbers? Well, other fractions. Let's go through a couple of those. So it's very easy to know that 5 to the 2 is 5 times 5. And 5 to the 3 is 5 times 5 times 5. And 5 to the 4, etc., etc., etc. But what if you start going backwards? What if, as I always said to you, you have to imagine numbers have a 1 in front of them as a multiplier, 1 underneath them as a denominator, an exponent 1. And I always said it helps if you think of any number that way. For instance, the number 5 isn't just 5, it's actually 5 over 1. But we never write that part of it because we can't be bothered. It's essentially saying there's 5 wholes of 1. And we would just only ever write 5 because it doesn't make sense to write 1 times 5 to the power of 1 over 1. And all of these 1s exist, but we don't write them mathematically because we don't want to waste time. We write it as a 5. So all numbers always, when it's just 6, it actually is 6 to the power of 1. When it's just a 7, it's actually 7 to the power of 1. When it's just an 8, it's just 8 to the power of 1. And that just means you're not multiplying it by itself any more times than just the 1. So you just have the 8. Well, they used a notation for a number 0 as well. Any number, it doesn't matter what the number is, any number on this planet to the power of 0 will always equal 1. They all equal 1. Doesn't matter. So any number to the power of 0 will equal 1. And this is an interesting thing because your professor might throw tricks on there that's like, what's 3 to the power of 3 that then is made to the power of 4, and all of that is made to the power of 5. And then at the end he goes, and all of that is made to the power of 0. You can ignore all of this because no matter what it comes to, when it comes to out to the power of 0 is the last thing, it's all going to be equal to 1. Because anything to the power of 0 is equal to 1. And oddly enough, if I then put out another bracket and say, to the power of 5, because of all this inside became power of 1, well, 1 to the power of 5 is still just 1. So all of these afterwards also won't matter at all. So I've seen a couple tricks in this book where they have, what's this? To the power of this, to the power of this, and then they sneak a 0 in there. And then they go, and to the power of 7, and to the power of 8. Well, that 0 makes all of this 1. And then all of this doesn't matter anymore. It's all still going to be equal to 1. So watch for little tricky situations like that. And one thing you're going to have to memorize is that any number to the power of 0 is 1. It doesn't matter what the number is. It's equal to 1. Well, that's great. But what happens when we start getting into negative numbers? What do negative number exponents even mean? Well, remember when I said any number is simply that over itself, but we don't write this part of it? Well, I want you to think of that part when we start putting a negative 1 exponent. Because now, this negative 1 converts this entire number into this. Or just that. So this negative number essentially says, take this number, send her to the denominator, and that's what it has as an exponent down there. Why did I mention the 1 as an exponent? Because if you have this, what about, remember that 6 over 1, to the negative 2? Well, that's the same as take this number, send it to the denominator, and it's now to the power of 2 down there. How do you resolve that? What's 6 to the power of 2? It's 36. It's 36. So this is the actual fraction answer of what is 6 to the exponent of negative 2. So if I was going to write that down mathematically, it would be like this. Hard to fathom unless you take the steps. So the first step, the negative exponent means it's now down at the denominator as the same exponent. Then you resolve it. 6 squared down here, staying in the denominator, 6 times 6. This is the final answer. And that's true for all of whatever I put there. So if I say 7, let's do 2 to the power of negative 3. Well, that's the same as 1 over 2 to the power of 3. See, when it goes down here, it becomes a positive 3 exponent. And that's the same as 1 over 2 times 2 times 2. And that's the same as 1 over 8. So 2 to the negative 3 is actually 1 over 8. And to figure it out, you just simply, it doesn't matter what that number is. So if I have 10 to the negative 3, it's the same as 1 over 10 to the positive 3, which is the same as 1 over 1 with 3 zeros. So 10 to the power 3 is 1,000th. That's why we could often say, we will often in scientific notation write this instead of writing this. Let's get to that, the decimal format of what that means. Okay, let's go through all our 10s. 10 to the 3, that's easy. It's 1 with 3 zeros. 10 to the 2, that's easy. It's 1 with 2 zeros. What's 10 to the 1? That's easy. It's 1 with 1 zero. What's 10 to the 0? That's easy. You told me. It's 1. What's 10 to the negative 1? That's the same as 1 over 10 to the power of 1, which is the same as 0.1. Oh, look. Our decimal was traveling 1 over each time. So to get to here, it was traveling 1 over. To get to here, it traveled 1 over. Remember, our decimals after the number. There's always an invisible 1 decimal there. And then to get to there, it was 1 over. To get to there, it's 1 over. What is 10 to the minus 2? Well, it's the same as 1 over 100, which is the same as 0.01. Now, I want you to notice that 1 over the 100 is actually should have been converted to 1 to the over 10 to the power of 2, which became 0.01. And I want you to notice that the zeros, the way we count up this decimal now, it used to be just adding zeros to the end based on the decimal, but now it's looking at how many decimal places happen. How many decimal places? So 1, 2. Okay? So if you want to look at it as number of zeros, you could include this 0 and this 0 as number of zeros. Let's test that theory. What is 10 to the negative 4? It's the same as 1 over 10 to the 4. And according to my theory, that's 1, 2, 3, 4 zeros. And that's true if we take the decimal place here. So 4 times 10 to the power, oh sorry, that should be a 1. So 1, if it was 1 times 10 to the power of 1, it would be 1. If it was negative 1, it would be here. If it was negative 2, it would be here. If it was negative 3, it would be here. If it was negative 4, it would be here. Okay, that's a good way to remember it. Whatever exponent is down here for a 10 base, we just go 1, 0, 2, 0, 3, 0, 4, 0, and then we put our 1. But in reality, it's about this decimal moving 1, 2, 3, 4 spaces. Okay, let's test this out a bit more. So now we have several formats. We can see that, well, 10 to the power of 3 is 1 with 3 zeros, and that 10 to the power of negative 3 is this 0, and 3 more, 3 total, 1, 2, 3 zeros, and then this 1. Well, great. That's great. That's good to know. So I have a way of expressing big numbers above 1 here and decimals here with this weird exponent. Yeah, I do. Let's look at, what about if I follow my rule and I said 10 times, and let's look at 10 to the power of negative 4, which is 0.0001. See, there's 4 zeros. Or if you want, the decimal place was here and went 1, 2, 3, 4. Okay? But let's look at what we know about our exponents, which means if I have the same base and I multiply it by another with the same base, but a different exponent, I can just add these exponents together to figure out what the actual answer is. Yes, you can. We have the same base. 3 plus minus 4 is the same as 3 minus 4, which is minus 1. So the answer to this is 10 to the minus 1. Does that make sense? Yeah. Yeah, it does. I got 10 to the minus 1 here. Let's look at another way of figuring that out, knowing that this is true. If you take a calculator and you take indeed 1,000, which is 10 to the 3, and you take this one, which we just discovered was 0.001, and you take this number and divide it by this, you will indeed get 10 to the power of 1, or 0.1. Okay? 1 0, or 1 decimal place. So you can prove that to yourself with your calculator. Now that we know multiplication rules, let's look at division rules. Can we use the same thing? You know, if I have 5 to the power of 2 and I multiply it by 5 to the power of 3, we know now it's the same as adding the exponents. Can I do a rule where if I have 5 to the power of 7, and now instead of multiplying it, I divide it by 5 to the power of 5, and now instead of adding the exponents, I subtract it? Let's look at that by breaking it down. What is 5 to the 7? So I'm saying that my answer will be simply taking this exponent and subtracting this, and the answer is going to be 5 to the power of 2. But let's break it down logically. What's 5 to the 7? It's 5 times 5 times 5, 7 times, right? So there's 5 times, 6 times, 7 times. And what's the bottom? Well, I'll just put it starting here. It's 5 times 5 times 5, 5 times, right? Okay, now my rule is for fractions that I'm allowed to cancel out anything from top and bottom as long as they're all multiplying each other. They are. Canceled, 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 canceled. Essentially they become ones. Canceled. So I got nothing at the bottom except the number 1 and nothing here anymore. And I'm left with 5 times 5, which is the same as 5 to the exponent of 2. Oh, so this rule will work. Let's go back to what I just did with my 10s with exponent of 3 times a 10 to the negative 4, and I said I can simply subtract these, and I came up with 10 to the negative 1. But let's say I put them in fraction forms. Peter, didn't you tell me that 10 to the negative 4 is the same as 1 over 10 to the positive 4? Yes, it is. That's right. And therefore at top, 10 to the power of 3, I have 10 times 10 times 10, and at the bottom I have 10 times 10 times 10 times 10. Well, these cancel out, so I'm left with 1 at top over 10. 1 over 10 is the same as 10 to the negative 1, because it's 1 over 10 to the 1, is the same as 0.1. So we can see that if we express it as a negative exponent, or if we express it as a division of the positive exponents, see this is the same as that, it's just at the bottom denominator now, we can use the same subtraction rule to get 10 minus 1 as we can for the addition rule if we're multiplying bases. That's exactly true. You will get the same answer. Will that work for other bases? Yes, it will. 5 to the exponent of 3 times 5 to the exponent of 2, to my theory, is 5 to the exponent of 5. I've proven that. But what if I have 5 to the negative 2? My theory is that I will simply subtract them and get 5 to the 1. This is true because 5 to the negative 2 is the same as 1 over 5 to the 2, and that's the same as having up top 5 times 5 times 5 and 5 times 5 at the bottom. This cancels out, this cancels out. I'm left with just 5 up here. So I'm left with just 5 to the power of 1, which is just 5. So that works. Well, will it work for the division rule too? Of course it will. We essentially just proved it. 5 to the power of 3 divided by 5 to the 2. I just take the 3, subtract the 2. They have the same base. And so 3 minus 2 is 5 to the 1. Because this is a bigger number than that, then it's like that. There's nothing at the bottom anymore. That will work for anything that's the same base. So if I have 7 to the power of 4 divided by 7 to the power of 2, it's the same as writing it as 7 to the power of 4 times 7 to the power of negative 2. According to my rule here, I add them together, I get 7 to the power of 2. According to my rule up here, I subtract them, I get 7 to the power of 2. I got the same answer, different path, but same rules. So what did we learn? When you're multiplying numbers that have the same base, you're allowed to add their exponents. When you're dividing numbers that have the same base, you're allowed to subtract their exponents. Great. Anything else? Yes. Yes, there is. There's one other rule, and it's this. So we've learned that something with a positive exponent simply means it's multiplying itself. Something with a negative exponent means it's multiplying itself, but at the denominator. Yeah? What about with something with less than 1 as an exponent? What does this mean? 5 to the half. 5 to the exponent of the half? I have no clue. What it actually means, and I'm going to use 25 to the half, it actually means square root of 25. Anything with a half fraction, 1 over 2, it means that this 2 is actually here. By the way, a square root usually has a 2 here, which just means you're square rooting it once. And so this this half tells you got to square root whatever's here. Okay, that's fine. But what if it was a third? Well, then you'd have to cube root 25, which means find the square root of 25 and then the square root again. We're looking for a number. So in this case, let's use a number we can actually cube root, which is 125. 125 to the third is the same as the cube root of 125. What is the cube root of 125? Well, it's a number that multiplies itself 3 times to get 125. That would be 5 times 5, which makes 25, times 5, which makes 125. So the number 5 times itself 3 times will make 125, which means the cube root of 125 is 5. So the cube root is, we're trying to find a number times itself 3 times that will equal that. Now that's tough to figure out sometimes because not everything has a perfect cube root, and we'll get to that. But the essential rule is, if I have a number and I have a fraction over it, let's take a different number, 625, and I have a fraction over it that's a quarter, it's the same as saying what's the cube root, not cube root, quarter root, which would be quad root, I forget what the term is, of 625. By the way, so it's what number times itself 4 times will equal 625. And in this case, it's the number 5 again. 5 times 5 makes 25. Times 5 makes 125. Times 5 is equal to 625. So the quad root of 625, or 625 to the quarter, is the same as 5. It's saying find me the quad root of 625. So that's what fractions mean. Well, what about, Peter, what about something that has both an exponent and a fraction? Well, you're allowed to go either way with this. You can find the cube. Actually, let me make sure of that. What is the square root of 25? Square root of 25, we already know is 5, right? And times itself 3 times is 125. So according to my theory, that's going to be 125. Let us find out. So I'm going to take 25 and I'm going to make it to the exponent of 3 divided by, I'm going to have to do it brackets, 25 to the exponent of brackets 3 divided by 2, close brackets, is equal to, yep, it's 125. So let's check that out. Do 125 times 25 and then take the square root. That's not correct. 25 times 25. And then I'm going to take the square root. 25. Yeah, it works out. So you can do it either way. You can first take, you know what, you can break it down as this. That's the same as 25 to the 3 times, I don't know if you can do 25 times 25 to the half. No, you can't. You can say to yourself, well, first I'm going to take the half part of that, which is the square root. So that's equal to 5. And then I'm going to take the cube of it, which I know is 125. Or you can go the other route and say I'm going to take 25 over 3 halves. I'm going to make 20. I'm going to find the cube root of 25, which is 25 times itself 3 times, which is 15,625. And then I'm going to find the square root, or put the exponent of a half of that, which is also 125. So either route will lead you there. You just have to do one first, and then the other to whatever the result was. So again, it's a little confusing, but essentially 3 to the half, use 9 to the half, means the square root of 9, which is 3. Okay? 9 to the 3 halves is also the square root of 9, but then whatever you get, 3, we're going to cube it. Cube, which is 27. So that's how we do these notations. And you know what? You can do any fraction up here. You can say, what's the square root and then the exponent of 9, or what's the 3 to the 9 over 2, so you can find the square root of 3 and then put it to the exponent of 9. All that. You can even have weird, stupid stuff like, what's 3 to the negative half? Well, I know that a half normally would be a square root. But, or let's use 9. What's 9 to the exponent of negative half? And you'd say, well, I know normally that means square root, but the negative means I'm going to go down to the bottom. So it's the same as 1 over 9 to the positive half. And I know that means square root. So that's the same as 1 over square root of 9, which is the same as 1 over 3. And indeed, if you take your calculator and you tell it to do the exponent of negative a half, it will spit out 0.33333, which is the same as the third. So these are just some rules. And we're going to go over some evaluations of what they want you to apply the rules to. All right. These are just warm-ups. Let's start with the first one. Evaluate, it says. Okay, we're going to start with this one. 7 squared is the same as 7 times 7. That's all the squared means. It's 49. Let's go to B. 2 to the power of 5. That's a pain. So B, 2 to the power of 5 simply means 2 times itself 5 times. Your calculator can do it, but we're going to do it bit by bit. 2 times 2 is 4. Times this 2 is 8. Times this 2 is 16. And times this 2 is 32. So the answer is 32. And your calculator will spit that out. It's 2 times itself 5 times. What about C? C is 5 to the negative thing. Well, remember that 5, any negative exponent simply means we now send it to the denominator, and it's 5 to the exponent of 1. 5 to any to the 1 is always just the number. Okay. D, we have something to the 0. Well, I remember the trick you taught me. Anything to the 0 is equal to 1. Anything. Anything to the 0 is equal to 1. Boom. That's an easy answer. 100 to the power of 2. I don't know why they threw that in there, but it's 100 times 100. Okay? Which is 10. 4 zeros, 10,000. Number of zeros 2, number of zeros 2, number of zeros 4. Great. By the way, you can also say 100 squared is the same as 10 squared, which is the 100, all squared. Now I know my rule of exponent to an exponent. I multiply that. It's the same as 10 to the 4, which also is 10,000. 4 zeros. Same thing, same result, same rules. And finally, the last one, this one here, 2 to the negative 3. Well, I just said anything with a negative exponent, you simply send it to the bottom with the same exponent but positive. 2 to the power of 3 is the same as 2 times itself 3 times. So it's 1 over 2 times 2 times 2. That's 4 times 2. It's 1 over 8. That's what 2 to the power of negative 3 is. Okay, now we got a few more coming up, and most of them are just testing our abilities to think logically. So now we're going to go on to 2. Okay, let's look at this first one. Well, minus 3 to the 2, you might start thinking, what does the negative mean? It simply means we follow the rule of exponents, which says it's minus 3 times negative 3. Well, a negative times a negative will always be a positive, and 3 times 3 is 9. So, minus 3 squared is that. Why do they give us that? What's the point in that? Well, they're trying to teach us a lesson about even exponents, because the next one is not an even exponent. It's a cube. And you might say, oh, it's going to be positive something too. But no, break it down. Minus 3 to the third is minus 3 times minus 3 times minus 3. Let's break it down. What's minus 3 times minus 3? We already established that. It's plus 9. But now we're multiplying it by a minus number. So a positive number times a minus number is going to be a minus. What's 3 times 9? 27. So negative 3 to the power of 3 still stayed negative. That's something that you have to notice. And the rule for that is any exponent, when you have a negative number and it has an odd exponent, the odd would be 1, 3, 5, 7, 9, 11, 13, 15, odd numbers, it will stay negative. It will stay negative. And when you have something with even exponents, minus 3 to the power of 2, or to the power of 4, to the power of 6, to the power of 8, power of 100, that's an even number too, power of 200, that's an even number, it will end up positive. So you have to look out for that. So negative numbers, if it's an odd number, it will stay negative, and if it's an even number, it will stay it will become positive. But wait, how do I figure out, like, if I have minus 3 to a giant exponent, how do I know if it's even or odd? Well, always look at the last number. If the last number is 1, 3, 5, 7, or 9, it's odd. If it's 0, 2, 4, 6, or 8, it's even. Doesn't matter the size of the number. It always follows that rule. And again, if it's odd, you keep the negative number, and if it's even, it becomes positive, and now you just got to figure out what the 3 is to that exponent. So they're just trying to, that's what this is trying to teach you, is what's the rules of exponents. Now this one, I think they're trying to distinguish where the minus is. I don't think they did a very good job here. I think what they're trying to say is that the minus stays in front of the squared, but in reality, when you write it like this, it should still be considered this. The minus would not stay out. If they really wanted to show us that the minus stayed out, they should have put the minus outside and the 4 like that, which is what I think they're trying to do. And I think what they're trying to say is this minus is going to get applied no matter what happens to in here. So 4 squared is 16, and then you apply the minus. But in reality, if they wanted to express that correctly, they should have put the brackets around the positive 4. As it is, when you write like this and you don't do that, I still consider this minus 4 squared to be 16, positive 16. It depends what their notation they're trying to show here. I can't see why they would put it unless they're doing this weird trickery, because they repeat the same questions twice. So let's take one that we know for sure, which is this one, and ask ourselves, what's negative 4 to the power of 2? Well, it's the same as negative 4 times negative 4, which is positive 16. So then they take a similar one here. They say, but what about negative 5 to the power of 3? What did I say about odd exponents? It's going to stay negative. So we know we're going to end up with a negative. 5 times 5 times 5, which is the power of 3, that's 125. So that's the answer. The negative number stuck around because of the odd exponent, and 5 to the power of 3 is 125. This one here, I think they're just trying to say that the minus applies after you do the exponent. I'd like to check the answers back there to see if that's what they're saying, but that's a stupid way of writing it. It should be like this. If you want the minus to apply after the exponent is done, that's how you would write it. You would have solve the bracket first and then apply the negative. BEDMAS. That's why I use BEDMAS. I think it's because they're saying the exponent applies here before the negative 1 in front of it is applied. It's a bad way of writing it, though. Okay, and here's just a little thinking question. Predict whether this exponent will be odd or even, or will be positive or negative. Let's have a look at it. Will minus 5 to the power of 120 be positive or negative? Well, power of 120, let's look at the last number. It's a 0. 0, 2, 4, 6, and 8 are all even numbers. Is this an even number? Yes. So that means any negative that has an even number exponent will become positive. So the answer is positive. Explain how you know, because 120 is an even number. Then let's move on to this one. They want us to evaluate these, and we're going to use some of the rules that we just followed. Okay. What is 3 to the power of 2 to the power of 2? Well, I've told you that when it's an exponent of an exponent, we multiply them. So it's going to be equal to 3 to the power of 4. Let's use our multiplication rules to test that out. What is 3 to the 2? So I'm saying it's going to be 3 to the 4. What is 3 to the power of 2 squared? It's the same as 3 to the power of 2 times itself. 3 to the power of 2. What did I say about multiplication? Exponents that have the same base? We can simply add them. 2 plus 2 is 4. Same answer. Different method. So we can see that it works. And you might say, well, it's confusing because 2 plus 2 and 2 times 2 are both 4, and you're right. They should have used a 3 here. Let's do that. Let's use a 3 to show that it's a little more clear than they're showing. Let's pretend this said to the 3. Well, I'm saying by my rule you take 2 times 3 and it becomes 3 to the power 6. But if you want to use the multiplication rule, it's the same as 3 times 3 to the power 2 times itself 3 times. And the multiplication rule says we can now add these exponents because we have the same base. 2 plus 2 plus 2 is 6. Same answer. So we can see our rules do indeed work. Okay, let's go to B. What is 7 to the power of 2, but then to the power of 4? Well, according to my rule, an exponent of an exponent, you simply multiply. So it's 7 to the power of 8. Let's use the multiplication rule to see if that's true. 7 to the power of 2 to the power of 4 is 7 to the power of 2 times itself 4 times. And now the multiplication rule says I can just add these. 2 plus 2 plus 2 plus 2, 7 to the power of 8. It works both ways. That's how you know this system works, is because you can test it out using the other system. Okay, let's go to this next one, which is interesting. They finally put the negative inside the bracket. I guess that's the point, is that when it's inside the bracket, it applies first. When it's not, it doesn't. So you always start inside the bracket. We've got minus 4. It's being squared, and then it's being cubed. So we can say that it's going to be minus 4, and the rule is 2 times 3 because it's an exponent of an exponent. So it's going to be minus 4 to the power 6. If you wanted to, and by the way, that's going to come out as a positive number because we have an even exponent. If you wanted to test it out, so I'm saying it's minus 4 to the power 6, you can break it down. It's minus 4 to the power of 2 times itself 3 times. Okay? So it's minus 4 times minus 4 is positive, but then times minus 4 is negative. So you get minus 4. And then 2 plus 2 plus 2 is 6. Same answer. So we're going to skip stretching it out now that we've proven exponent of exponent works. We're going to do this one. Minus 10. Now they're saying, here they're saying that minus doesn't apply to what's in here, but it will apply to this exponent. So we're talking about 10 to the power of 2 is going to be a minus 100 to the power of 3. So you might think that this is going to be equal to a minus 10 to the power of 6, and then you'd say, well, it's going to be an even number. But it's not actually, because it should be minus 100, like it would be a positive, let's see, it would be a minus 100 once that's resolved, cubed, and the minus to an uneven number is going to be an odd number. So I think you have to then write it like this, that it's going to be a minus 10 to the power 6, because that minus will apply afterwards. And you might say, well, no, it gets cubed. Yeah, you're right, it does get cubed, but cubed keeps it a minus in the end. So logically you've got to figure out what your final number is going to be. That's a little tricky, that one, and a little tough to fathom until you rationally say, okay, well, this gets squared, and then this minus applies to it. So it's really minus 10 squared like that. And then the cubed, because this is minus, and I know minuses will stay cubed, I can just go ahead and write my minus, and then in brackets say 10 to the 6. So it's where you're defeating the even rule. I believe that's the answer. You might want to check in the back of your book. E is just showing us an exponent of an exponent of an exponent, and it really doesn't matter because it'll still work. So it's saying, what's 2 to the power of 2 to the power of 2 to the power of 2? So my rule is an exponent of an exponent of an exponent. We multiply them all out. So 2 times 2 is 4, times 2 is 8, and it's going to be 2 to the power of 8. But we can also test this out. What is 2 to the power of 2 to the power of 2? Well, it's 2 to the power of 2 times itself. And then all of that to the power of 2, well, it's all of that times itself. Okay, using my multiplication rules, I can add them. 2 plus 2 plus 2 plus 2, 8. So an exponent of an exponent of an exponent, they all still get multiplied. Here's an interesting question. What if I take 2 to the half and I make it to the power of 2 and I make that to the power of 2? Can I use my multiplication rules? Yes, you can. You do a half times 2 over 1 times 2 over 1. Now the beautiful thing about multiplication is you simply multiply the top and multiply the bottom, and that is your new fraction, and beautifully 4 over 2 can resolve to 2, so the answer to this question is 2 to the power of 2. And you might say, what? The answer to that's 4? Yeah, let's just prove that. Let's put that to the side. Okay, so I said 2 to the power of half to the power of 2. So let's do it logically. What is 2 to the power of half? Well, I said it's the square root of 2. To the power of 2, squared, and to the power of 2. So let's start with the 2 to the half. That's the same as the square root of 2. Okay, and I'm squaring it, right? Yeah, so it's times itself. What is a square root times itself? It's simply the number. So the answer there is the number. And then all of that gets squared again. 2 to the square. Oh, that's the answer we got. Yes, it was. So multiplication still works for an exponent of an exponent of an exponent, even when there's a fraction. Will it work with negative? Yes, it will. Yes, it will. You just multiply them out. You keep track of your negatives. It will work. Okay, well, let's see. Do I get all my homework back? Now I lost it like a fool. Okay, let's go on. Oh, okay, here's one of the tricky ones that they mentioned. Remember when I said sometimes in your book they're going to throw it all with an exponent of 0 on the outside and you could waste all your time? Well, the only thing to notice here is that this minus is outside all of these brackets. So that means you solve this, and then that, and then that, and then you apply the minus 1. Well, we could bother with this, and we could bother with that, but all of that in there is going to be put to the power of 0. And anything to the power of 0 is 1. And then we apply the minus. So the answer is minus 1. And the reason we apply the minus after is it's well outside the brackets, and exponents come first in BEDMAS. So we have to do the power of 0, and then apply that minus 1, which is the same as saying minus 1 times all of that. So since all of this here resolves to 1, this minus gets applied afterwards. Tricky and annoying, I understand. All right, let's look at these, and let's look at them in a way that we can understand them, okay? So we're going to look at these, and we're going to go like that. Now, these might always seem annoying and tricky, but I want you to understand this. 49 square rooted squared. How did we used to get rid of our square roots? We used to square them, and that would just essentially wipe out what was there and leave the number. So whenever you have a square root and then it's squared, it's simply whatever the number is. So in this case, the square of 49 square root is simply 49. But if you want to see it using the proper exponents, didn't we just learn that the square root symbol over here, it can also be expressed as a half fraction, so that 49 to the half is the same as that square root? Yes, it is. 49 to the half is indeed that square root. And all of it's put to the exponent of 2. And didn't you tell me that I can multiply exponents? So I got 1/2 times 2 over 1, which is equal to 2 on the top and 2 on the bottom, and they simply cancel out to 1. So I would be left with 49 to the power of 1, which is 49. Oh, So that explains why the square root and the square cancel each other out. Fraction-wise, it all becomes 1, 49 to the 1, simply the number inside. So we've learned importantly that whenever you take the square of a square root, all you're doing is getting rid of the square root and the square, and you're left with the number inside as the answer. Good to know. What about this next one? Why did they give it to us? That's a good question. Let's maybe examine if 64 can be expressed in any terms of 3. Well, I know the square root of 64 is 8, so the answer to that is no. And we have 3 times 8, which is 24. So that's actually the answer. I'm not quite sure why this one is there. It's a little bit weird. It would be better if this was some number that we could turn into 3, so that we could show that the 3 to the 1 times 3 to the half or whatever gets our same answer. But as it is, the square root of 64 is 8. 3 times that is 24, and I'm not sure if that's what they were going for. A little bit odd. Let's look at the next one, though. The next one simply has, and let's do 2 ways. We cannot multiply them normally unless they had the same base, but we will be able to multiply them in a bit. Let's first evaluate the square root of 4, it's 2, and evaluate the square root of 16, it's 4, and what's 2 times 4? It's 8. So the answer to this whole thing will be 8. But let's see if we can express it in other ways that make sense. Okay, what's a way that 4 can be expressed inside of that? Well, 2 squared. That's correct. 2 squared. 2 squared to the square root is the same as 2 to the 2 over 2, or just 2 to the 1. It would just be a 2. But yeah, that's one way of looking at it. It's the square root. It's 2 to the square root of 2 to the 2. What about 16? Well, 2 times 2 times 2 times 2 is the same as 16. So we get the square root of 2 to the 4. Am I allowed to just multiply these square roots now that they're the same number? Yeah, I am. I'm allowed to now do the square root of 2, and when I'm multiplying the same numbers now, I just add up their exponents, so it's 2 to the 6. Very confusing, I know. Now, am I allowed to say that that's the same as 2 to the 6, and instead of square root, say it's to the half? Yes, I am. Am I then simply allowed to multiply my exponents? So it's 6 over 1 times 1 over 2, which is 6 over 2, which is 3. Yes, I am. Okay, so that's the same as 2 to the 3, which is also 8. So a long root, that's certainly a long root, but it's just to show you that the exponent rules work all the way throughout it. I essentially made them both a base of 2 so that I could add their exponents, and then I turned the square root into an exponent of a half so that I could show that you could multiply them out and get the same exponent and the same answer. Well, they're kind of going for this at the next one, but let's go both roots. We're going to resolve it, and we're also going to do the long root. So the square root of 9 up top obviously is 3, and the square root of this down at the bottom is obviously 9, and we're going to end up with 1 over 3. But let's put it all in terms of stuff that we can understand. So the answer is going to be ultimately 1 over 3. Well, we can do the square root down below. We can turn 9, and actually we can just leave it as 9 if we want. We can leave the top the same, and the bottom we can turn 81 into a square root of 2. So now we have 1 square root of 9 to the 1 divided by square root of, actually that might, yeah, no, that still works. So when I have a division of 2 exponents, I subtract them. What's 1 minus 2? Oh, it's the square root of 9 to the negative 1. Okay, well, actually that might have made it incredibly confusing, so I'm not going to do that. I'm going to instead turn their exponents, so I've got 1, I'm going to turn their square roots into a half. And I'm going to do the same, except I'm going to turn 81 first into an exponent of a square of 9, and then I'm going to half it for its square root. Okay, so this is the same as 81, and this is the same as 9. And up top, I'm going to realize that I can just multiply their exponents, so 1 times 1/2 is the same as 9 to the 1/2 still. And then at the bottom, I can multiply their exponents. 2 times 1/2 becomes 2 over 2, which simply becomes 1. Okay. Now I have 9 to the half divided by 9 to the 1, and my rule says I can simply subtract their exponents. So half minus 1 is equal to -1/2. So I've got 9 to the -1/2. And I said before that a negative half, I know it's long and weird, but I'm showing you that the whole root can work. So I said that a negative simply means that you send it to the bottom. So now I'm left with 9 to the half. And I said that a half is the same as the square root. So we're left with this. And what's the square root of 9? It's 3. Long way to get to the same answer, but you can see that all the exponent rules still worked to get to there. Okay? All the exponent roots still worked to get to there. And I could have even put it in terms of base 3, which would have been really annoying. But if you want to see it also in another way, here's another way. Square root of 9 divided by square root of 81 is the same as square root of 3 times the square root of 3. You're allowed to do that. These would multiply out to 9. And down at the bottom, I can turn my 81 into square root of 9 divided by the square root of 9. Okay. I'm not using the exponent rules, but I'm still using sort of logic of the square root rules. Okay, didn't I just say that a square root of 9 could be turned into this? And I have 2 of them, so I'm going to be left with square root of 3 times square root of 3 up top. And I'm going to be left with square root of 3 times square root of 3 times square root of 3 times square root of 3 down at the bottom. Well, these two can be canceled out. So I got 1 up top. So I'm left with 1 over square root of 3 times square root of 3. And a square root times itself is simply 3. Same answer. Long root, but it's just to show you that all these rules still work. Now the other skill that you're going to have to remember is how to add fractions, because that's going to be a big part of this. And you cannot add fractions. So unfortunately all these rules have to be memorized. There's no way around it. You're not allowed to add fractions. You're allowed to multiply fractions no matter what's at the top and bottom, but you're not allowed to add them unless they have the same common denominator. Now you can find a number that's common between 3 and 8 if you want, or you can simply multiply the bottom, multiply its top by its bottom, multiply its top by its bottom. So if we do that rule, what's 3 times 5? We're left with 15. What's 5 times 8? We're left with 40. And what's 3 times 8 on the bottom? We're left with 15 plus 40 up top divided by 24. What's 15 plus 40? It's 55 divided by 24. Is there a way to simplify it? No. This can be divided by 11 and 5. This can be divided by a whole bunch of things, but not 11 and 5. So that's called cross multiplication. You take this denominator, you multiply it by the numerator. It goes down here, and it becomes 15 over 25. And then you take this denominator and you multiply it by its numerator, you get 40 over 24. Now they have the same denominators. The denominator just stays the same, and you add the numerators. That's how you add fractions. You divide or multiply fractions or subtract fractions in a similar way. So here they want us to subtract the fraction. Well, I already know that 3 and 8 don't have anything in common, but I'm going to cross multiply. So I get 15. And then I'm going to cross multiply, and I get minus 40, same numbers. And then I multiply these bottoms, and they become 24. So what's 15 minus 40? It's minus 25. And the denominator is just that. So it's actually the same as minus 1 and 1/24. That's the whole number answer, and that's the fraction of the answer. But that's how you have to subtract them. They must add or subtract, have the same denominator. Well, there's the other complicated rules with fractions is multiplying, or dividing rather. Anytime you see it like this, or perhaps you'll see it like this, a big division bar here in the same numerator. Whenever you're dividing a fraction by fraction, it's the same as multiplying the reciprocal. Multiplying the reciprocal of the second fraction. So like that. Change the division to a multiply and flip the fraction. So you get, now multiplying fractions is really easy. You just multiply the top and the bottom. So you get 21 over 16, which by the way is the same as 1 and 5 over 16. It can't be really simplified more than that. But see, once you figure out how to multiply them, multiplying fractions is the easiest thing on the planet. What about, you got these multiple steps here? Well, follow your order of operations. The multiplication must take place first, and you must consider this minus as attached to this number. So let's just move this part away a bit and consider this negative attached to the negative 3. So we simply multiply the top and multiply the bottom, and you end up with minus 12 over 24. Now we can go back, and we are doing 1/5 minus that number. Well, 24 has nothing in common as 5, so we cannot subtract it. And we could not have done it before. We'd have to multiply this out before we subtract it. So we have to do cross multiplication. So 24 times the top is 24. 5 times the negative 12 becomes negative 16. And their denominators become, 5 times 24 is 120, I think. So these become their denominators. So 24 minus 60 is the same as minus 36 over 120. Both these fractions can be divided by 2. So I get minus 18 over 60. Oh, they can be divided by 2 again. So I get minus 9 over 30, and that's it. Nope, they can both be divided by 3, which is minus 3 over 10. So it turns out that this original fraction could have been divided by, let's see, 2, 2, and 3, which is 12. So yeah, that can go in there, and that can go in there, minus 3 over 10. That's the answer of this big mess. A lot cleaner like that, minus 3 over 10. But you have to multiply them out and follow your rules before you can subtract them, and before you can subtract any fractions, they must have the same denominator. You can see multiplying is a lot easier. What about this next one? They've got a whole bunch of rules in there. Yep, they do. You just go step by step. So BEDMAS, brackets first. What's going on in the brackets? A division of the fraction. So what's the rule? We take the same first fraction, but instead of division, we multiply the reciprocal of the second fraction. So the 12 went up top, and the 5 went down below, and we multiplied. Okay, let's start with that. That's simple. We multiply the top, and we multiply the bottom. We get 108 at top, and we get 50 at the bottom. Great. So this whole thing came to that. So let's just replace it with that. That's why you go step by step. Okay, are we adding or subtracting or what? Well, we're adding a negative version. So let's associate that negative number with one of the numbers. So let's associate with the top number. So we're adding them. We can't add unless what? They have the same denominator. I can't really see the same denominator, so I'm going to cross multiply. Multiply this, I get minus 200. Multiply this, I get plus 324. And this is over 150, and this is over 150. How did I get this denominator? Well, you multiply the bottoms. That's how you figure out a common denominator when you cannot figure out an easy way to do it. Just cross multiply. So I got minus 200 plus 224, which is equal to plus 24 over 150. Can those be simplified? Yeah, they can all be divided by 3. You're left with 8 over 50. Can that be simplified? Yeah, they can all be divided by 2. You're left with 4 over 25. That can't be simplified anymore. Yeah, I think that's it. Yeah. So that means that this original fraction here, instead of being divided by 3 and then 2, could have been divided by 6. So sure enough, that goes into 24 4 times, and it goes into 150 25 times. That is your final answer. Plus 4 over 25 is what happens when we take minus 4/3 and add it to that monstrous stuff that was going on in there. And you just follow the rules of BEDMAS every time. So what's going on in this one? Well, there's a bracket. Don't be mistaken. You might say, oh, I have to multiply it out. You could distribute this and then distribute that, and then you have to subtract this fraction from that fraction. But it's going to be a lot easier if you solve the brackets first. They do not have a common denominator, so you're going to cross multiply 3 times, and I'm just going to rewrite my brackets. 3 times 3 is 9, plus 8 times 7 is 56, and 8 times 3 at the bottom, so it's 9 over 24, plus 56 over 24, all of it multiplied by minus 10, 9 over 10. We can add them. 56 plus 9 is 65 over 24. So 65 over 24 is what's in the bracket. 65 over 24. Now you might say to yourself, do I want to simplify that? You might try, but I don't. You can if you want. If you can figure out a simplification. I can see this is divided by 8, but I don't believe this is divided by anything. So I'm just going to multiply them out. So fortunately, multiplication is a lot easier. So I multiply this and I multiply this. So I know my number's going to be negative because it's a negative. I know it's all going to be over 240 because I can easily multiply 10 times 24. And then this ends up being 545, and then 9 times that, 54, 50, minus 595, I think. And then I can look and instantly see they can both be divided by 5. So I probably could have simplified along here and simplified along here. And actually you can. Let's go back and do that. So my ultimate thing was 65 over 24. Okay, and I had this times 65 over 24. Okay. And I had a minus, and so let's just ignore the minus. If I divide this by 3, I get 8, and if I divide this by 3, I get 3. If I divide this by 5, I get 2, and if I divide this by 5, I get 8, I think. No, what am I thinking? That divided by 5 is 10, 11, 12, 13. So I'm left with these fractions. Minus 3 over 2 times 13 over 18, or over 8 rather. I don't think I can simplify anymore. So minus 3 times 13 is minus 39, and 2 times 8 is 16. They cannot both be divided by 3, or 4, or 16, or 1. So that's my final fraction. You can see why simplifying this was easier than trying to come up with the monstrous fraction that I would have ended up with. So you can sort of see how to divide things out. Great. Simplify. So we're just going to follow the rules of exponents, and then I'm going to stop the video, and I'm going to continue later with the questions at the back. Simplify. We're going to follow our rules. So what are our rules? The first one. What is a to the power of 5 times a to the power of 2? Well, they have the same base, so I'm allowed to simply add the exponents. So it's a to the power of 7. That's an easy one. What about b12 divided by b to the power of 12 divided by b to the power of 8? Well, sometimes it's easier to think of that fraction as that division when it's written like this. I find it that way anyway. And now the division rule is, instead of adding the exponents, I'm allowed to take this exponent and subtract this exponent. So 12 minus 8 is a positive 4, so I get b to the positive 4. And it makes sense that the b is the only one left standing, because this b to the 8 is less, so I'm going to have more b's up at top. So b to the power of 4 is the final answer. Well, then they're just making me practice my basic exponent rules here, because here's the exponent of the exponent rule. The exponent of the exponent rules, I'm allowed to multiply the exponents, so it's c to the power of 12 is the answer. What about this next one? What are they doing here? They got a d times a d times a d. Do they all have the same base? Yes. What's this first d to the power of? 1. What's the rule for multiplying fractions with the same exponents with the same base? I simply add their exponents. 6 plus 3 plus 1, so it's equal to d to the power of 10. Not that hard, that one. Determine the exponent that makes each equation true. this isn't just a visualization thing, it's just to help you. What 9 to the power of what creates an 81? Well, that's easy for you to quickly to see that 9 to the power of 2 is equal to 81. So therefore, x must be equal to 2 here. And that's what they want you to think of. What about the next one? Well, obviously 8 to the power of 8 is 64, not 256. We just have to figure out if 8 times 64, which would be 8 to the power of 3. So essentially I'm trying to find out if 8 times 8 times 8 is equal to 256. I know that 8 times 8 is 64. I'm going to do my long division. 8 times 4 is 32. 8 times 6 is 48 plus 3 is 51. 512. No, it's that's half of that. Huh, that's interesting. I wonder if it's 8 to the 3 and then, I wonder if it's like 3 halves or something weird like that. Or 3.5, or 2.5, 2.5. Let's find that out. I'm saying that it might be 8 times 8 times 8. I'm saying it might be 8 times 8 times a half. Now that'd be the square root of 8. I don't think that'll work. Square root of 8. So 8 times 8 times 8 square root. I don't think that'll work. No, it won't. Let's look at it in terms of, so they made this a little tricky. Let's look at it in the terms of 2. So 8 is the same as 2 to the power of 3, to the power of m, which is the same as, I'm allowed to multiply 2 times the 3m. Oh, that's a weird way to think of it, isn't it? And 2 times 2 times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64, times 2 is 128, times 2 is 256. 1, 2, 3, 4, 5, 6, 7, 8. Let's make sure and take our calculator and say 2 to the power of 8, 2 to the exponent of 8, oops, 2 to the exponent of 8 is indeed 256. So now I've got 2 to the power of 3m is the same as equals 2 to the power of 8. Well, if these are the same, I can now just say, when will 3m equal 8? Well, divide by 3. Divide by 3. M has to be equal to 8 over 3. That's bizarre. Now, that's in the power of 2, not in the power of 8. So if my m is 8 to the power of 3, well, no, I can just put I figured out my m. So let's try that. I'm saying that, wow, that was a tough one, eh? 8 to the power of 8 over 3 is 256, which is the same as saying 8 to the power of 8 divided by 8 to the power of 3. How did I do that? Well, oh no, sorry, that's not what it means. It's 8 to the power of 8 is the same as 8 to the power of 8. That is also not multiplied, but is it multiplied? 8 to the square, 8 cube root of 8? Might be multiplied. Let's just take that fraction, though, and take 8, and we're going to make it to the exponent, and in brackets, 8 divided by 3, close brackets, and see if we get it. 256. Indeed, m would have to be 256, which means the cube root of 8, the cube root of 8 to the exponent of 8. That's what the third means at the bottom. It means the cube root of 8 to the exponent of 8, which makes sense because I had to turn 8 into 2, which was the 2 cube root, and to find out the exponent of 8, to find out my m. Very complicated, but I had to figure out that this and this could both be expressed in forms of 2, which is 2 to the 3 to the m, and essentially 2 to the 8. So that I knew my m had to be 8 over 3. Weird. That one was weird. I'm surprised they threw that in there because that was a hard exponent. I think they meant one exponent up. I think they meant to throw you an easy ball. An easy ball, make it 8 to the power 4 or something. So here, when will minus 5 to what exponent become a minus 25? Well, we know it's got to be an odd number. What?
631.
Yeah, relax. 6 times, we know it's got to be an odd exponent because it's a negative number. So I'm going to test out 3. Negative 5 times negative 5 is plus 25. Times a negative 5 becomes negative 125. So indeed, my exponent, my m, must be 3. Then finally, what number, negative 10, is going to equal negative 100,000? So how many zeros are we talking? Well, it's going from 1. It's going 1, 2, 3, 4, 5, 6, 7, 8 zeros. And we know it's a negative number, so that doesn't... 8 zeros. So, oh, I see what they're doing. They're keeping the negative outside of that, and they just want the 8. And it's that weird notation thing. So we don't even use the negative. So because they didn't put it in brackets like this, they're saying that the negative just constantly stays outside, and you just multiply your 8. I don't like this notation. I think it's confusing. Yes, I did, and I said go away. And so the answer to this is r is equal to 8, because there's 8 zeros. So it's minus is outside, and they're saying 10 to the power of 8 first, and then you apply the minus after. All right. Talk to you later.